Let's think about where mins and maxes, either local or global, tend to occur. So thinking about just this graph, what can you say about what's going on at the mins and maxes? So pause the video and think about that. All right, you might have said at the mins or maxes, the slope of the tangent line is 0. You might have said, well, right here, the tangent line is just purely horizontal, and the same thing at the max, local max there, and the same thing at the local min there. So you might have said the slope of the tangent line is 0. Or you might have said the tangent line is horizontal. Or you might have said f prime is 0. I don't want to say exactly f prime of x equals 0 because f prime of x is kind of a whole function, but I could say like at this point here, which we'll call c, f prime of c equals 0. So what does this give you as an idea? If I wanted to find all the places where there was a local min or max, what could I do using the derivative? Well, you might say, to find all the mins and maxes, look for where the derivative is 0. So that's an idea. So then the question is that good? Does that find all the mins and maxes? Does that find things that aren't mins and maxes? So sketch a few graphs if you can, thinking about ways that this idea might break down. All right, so welcome back from pausing. So one idea you might have come up with is if you have cost here and some x range here, but maybe only a certain range of x values are feasible. So like you can only run your machine this slow, slower than that it shuts down, and you can't run it any faster than this. So we'll call this the range of feasible x values. It's possible that you would have a curve that looked like this. And let's say you were trying to find the minimum cost point. Well, you'd have a maximum cost point, which is usually not a good idea. The minimum cost point, is that happening where the derivative is 0? No, it's just happening in an endpoint in the interval. So we can say, oops, we should also check the endpoints of the interval if we're given a closed interval. Closed means square bracket, that last point is included here and included here. Open intervals we would draw with parentheses and draw with an open circle. So when the book says closed interval, it means including the endpoints there. And you might think, well, this is just kind of made up, that why would the cost be lower at one end or the other and higher in the middle? But that actually happens in really important problems that we'll see later in the chapter. So we should check the endpoints as well, because the slope doesn't have to be flat there. Any other kind of counterexamples to this idea you can think of? Pause the video. Okay, welcome back. Another one is that, let's say we were minimizing, we could have a function that does that has a sharp corner here, like almost like absolute value. So right there, what can we say about the tangent line? Well, the tangent line here has a positive slope. The tangent line here has a negative slope. There's no unique tangent line here. We could say that's a tangent line, but that's also a tangent line, and that's also a tangent line. So because there's no unique one, the derivative there does not exist. We wouldn't say the derivative is 0. We would say the derivative does not exist there. So these aren't just sharp turns, these are infinitely sharp turns. They're the intersection of two lines. And here, one of those points is actually our minimum, but another of those points isn't our minimum. So you might be wondering, where would we ever have a function like this? That actually happens in some applications, in particular deep learning, which is basically neural networks using the rectified linear unit, like the max of 0, x. There's a machine learning procedure called lasso. There's something called compressive sensing. That's really cool. And in all of those, we have objective functions that have absolute values or max 0 x's, and so we have these sharp turns in the objective function. So it looks like not only should we check where the derivative is 0, we should also check the endpoints and check places where the derivative does not exist. And then we should be fairly sure we'll find all the mins and maxes, but we might also find points that aren't mins and maxes. So there's a definition we need to know. Critical point, or value or number, which is a location where the derivative is either 0 or does not exist. So the endpoints don't count as critical points, but we still need to check them anyway. And some books say, well, the critical point is the point in x and y, the critical number is the x value, the critical value is the y value. We're not going to get too picky about it. So it's just locations. And what we really are interested in is the x value. Once you have the x value, you can compute the y value without too much trouble. It's finding that x value that's interesting. So our goal in chapter 3.1 is to be able to find the mins and maxes of a function without graphing. You might say, well, someone gave me a function, I'm just going to graph it, and I'm going to say, here's a min, here's a max, here's a min. But we're doing it this way for two big reasons. One, we're training for those higher dimensional problems where you can't graph. I mean, how are you going to graph something with 800,000 variables, for example? But we can still use the methods, some of the methods we're learning here, to help find mins and maxes in those higher dimensions. The other reason is, even if you do have just a one-dimensional problem, sometimes you want a general formula for where the min and max are going to happen. Not just a single answer in this case, but for all problems of a particular type. So you might ask, where are the mins and maxes of a quadratic? Can you give me an answer that involves a and b and c? So if someone gives me a new quadratic, I can just compute the minimum immediately without having to graph it. Or ax plus b over x, that happens in some industrial supply chain kind of problems. And there's others as well. This is particularly common in theoretical economics. Someone says, well, here's how a cost function goes. Let's find the actual the minimum as a formula based on parameters in the cost function. So here's our Calc 1 procedure for finding mins and maxes on a closed interval starting at A going to B. And remember, this is mainly us practicing methods that will hopefully somewhat work in higher dimensions. So that's why our first step is not to graph the function. The point here isn't to graph the function, say, here's the min, here's the max. It's to practice all this derivative stuff. So step 0 is do not graph the function that you're given. Step 1 is take the derivative of the function using formulas, all our favorite formula-based derivative rules. Then set that formula equal to 0 and solve for x. So we're asking which x values make f prime equal to 0. What we're not doing is just saying x equals 0. It's possible that that's a value where the derivative is 0, but that's not enough to find other places where the derivative might also be 0. And then we should also ask where is f prime non-existent, those sharp corners like this or like that, because those could be mins and maxes too. Then compute the y values at the x values you got in step 2 and step 3. Solving for x here can be a little complicated. It might involve the quadratic formula. It might involve reasoning like, oh, product of two things is 0, so either one of them has to be 0. So we compute those y values. We also check the y values at the endpoints. And then of all those values, of all those y values, just say the highest one is this, so that's the global min, or global max. The lowest one is this, so that's the global min on this interval. Now this doesn't tell us which ones might be local, or I mean, we might just get a point and not know whether it's a local or global min because we haven't checked right nearby it. So then once you've done all that, then that's when you graph to check. It's also kind of okay once you take the derivative formula here, you could graph that and have Desmos also compute f prime for you and graph that to make sure your derivative formula was good before you do the rest of this. So some people like to summarize this whole procedure with take the derivative, set the derivative equal to 0, and solve for x. But you can see that's actually only a small part of the whole thing. Where in here are we doing critical values or critical points? Take a sec to think about that. It's actually here, what values make f prime equals 0 or does not exist. So that's where we're finding the critical values. All right. You can tell we're kind of emphasizing doing things by hand, but when you're computing the y values and checking the endpoints, it's totally okay to have a calculator or Desmos or whatever do that for you. What we're mainly stressing here is doing the derivatives by hand, not the function evaluations. We'll just use whatever we can use for that. All right.